In this first problem we have f as a function that is twice differentiable, and that means that the first and second derivative exist for all real numbers. The table above gives values of x for selected points in the closed interval between 2 and 13. First thing we want to do is to estimate f prime of 4. So we're looking for the derivative at 4, but 4 is not one of our values here, and even if it was one of our values, the only thing we have in this table are values for the original function. We don't have derivative values here. So the best that we can do is to estimate the value of the derivative. And what we're going to do then is to use points to the left and to the right. And so the picture goes something like this. We're trying to find a derivative at a particular point. And that derivative is the slope of the tangent line to that point there. But again, we don't have a function to find a derivative of. So what we can do instead is to take a point a little bit to the left and a little bit to the right of it and find the slope of the secant line that passes through that point. And we can use that to approximate the slope of the tangent line at some point in between. So we'll use x equals 3, y equals 4, x equals 5, y equals -2. We say the slope of the secant line is f of 5 minus f of 3 over 5 minus 3, which is -2 minus 4 over 2, which comes out to be -3. With part B, we want to evaluate this function. It says integral from 2 to 13 of 3 minus 5 times f prime of x dx. And to do this, we're going to use our properties of integrals, which is to break this down. The first thing we're going to use is the sum or difference rule, which says that the integral of a sum or a difference is equal to the sum or difference of the integrals. So the first thing I do is separate the 3 and the minus 5 prime of x. And I'll just review this property over here, the integral of f of x plus g of x dx. And we can actually say plus or minus if it's a sum or a difference. So, and that's equal to the integral of f of x dx plus the integral of g of x. So the integral of a sum or difference is equal to the sum or difference of the integrals. Next, we're going to apply the constant multiple rule. The constant multiple rule says that a constant, the integral of a constant times a function, doesn't have to be 5, so it could be any constant a, is equal to the constant times the integral of the function. So basically a constant multiple can be moved out of the integral sign. And that's what we're going to do over here. Next, integral from 2 to 13 of 3 dx. This can be looked at in two different ways. We can look at it algebraically and see that that 3 is really 3 times x to the 0 power. Then when we perform the power rule for integrals, we're going to increase the exponent to 1 and divide by 1. And so that's going to give me 3x. I can actually use the constant multiple rule here again with this, but it's maybe simple enough that I don't need to do it at this point. So what I have is I want to evaluate 3x at 13 minus 3x at 2. 3 times 13 is 39. 3 times 2 is 6. And that gives me 33. Again, I could have written this as 3 times the integral from 2 to 13 of dx. And what that really means is that there's a 1 inside that. We assume a 1. Or we assume an x to the 0 power. To integrate, we increase to 1, divide by 1, and we just get x. Then we're going to evaluate x at 13 and subtract x at 2. And that's just 3 times 11, which is 33 again. So these are all different ways of looking at that. Now, graphically speaking, 3 is our function, which means it's just a horizontal line of height 3. And from 2 to 13, then, we have a rectangle of height 3 and width 11, which has an area of 33. Now for the integral of f prime of x dx, we use the fundamental theorem of calculus, which says the integral from a to b of f prime of x dx, just f of b minus f of a. So here we have 5 times f of 13 minus f of 2, which from the table is 6 and 1, and we end up with 8.